All right, let's go. Number 10. The Pulsar Timing Gravitational Wave Background. In 2023, the Nanograv collaboration in North America had spent 15 years doing something unglamorous. They were monitoring millisecond pulsars, the universe's most stable clocks, looking for tiny correlated timing variations that would signal the passage of gravitational waves through the galaxy. They were not hunting for anomalies. They were trying to confirm a signal that theory had predicted for decades and that no instrument had ever been sensitive enough to detect. Standard cosmological models predict that as galaxies collide and merge across cosmic history, their central supermassive black holes, objects of hundreds of millions to billions of solar masses, sink toward each other under dynamical friction, eventually forming binary systems tight enough to radiate gravitational waves. The cumulative effect across the observable universe should produce a stochastic gravitational wave background, a low-frequency hum permeating all of space-time, producing correlated timing shifts in pulsars separated by specific angular distances on the sky. The pattern of those correlations, the Helling-Downs curve, is the unmistakable fingerprint of a gravitational wave background and nothing else. In June 2023, Nanograv, the European Pulsar Timing Array, the Parkes Pulsar Timing Array in Australia, and the Chinese Pulsar Timing Array published simultaneously. The Helling-Downs correlation was confirmed. The gravitational wave background was real. The amplitude of the signal was 2 to 3 times higher than the models predicted from the known population of supermassive black hole binaries. The universe is louder than it is supposed to be. The proposals came immediately. Contributions from cosmic strings, one-dimensional topological defects left over from early universe phase transitions, could boost the amplitude. But cosmic strings require physics beyond the standard model that has never been confirmed. Primordial gravitational waves from the inflationary epoch could contribute, but primordial inflation models that produce this specific amplitude excess are not the models most favored for other reasons. A 2023 analysis in Physical Review Letters by Afzal and colleagues across the Nanograv collaboration named the excess and listed the candidate explanations. None has been confirmed. The most significant gravitational wave detection since LIGO's first event in 2015 arrived with a factor of 2 amplitude problem attached to it. Spacetime is ringing louder than every population of known sources can account for. Something is shaking the geometry of the universe harder than we can explain. Every pulsar in the timing array is recording it. We have confirmed the signal. We have not confirmed what is making it. The galaxy's most precise clocks agree on something impossible. The next glitch is closer to home. Number 9. The Black Hole Shadow Asymmetry. The Event Horizon Telescope collaboration spent a decade building the most ambitious instrument in the history of astronomy, a planet-scale radio interferometer using telescopes from the South Pole to Hawaii to Spain, phase-locked to atomic clocks accurate to 1 second in 100 million years. They were not looking for anomalies. They were attempting the first direct image of a black hole's shadow to confirm that the dark central region predicted by general relativity's Kerr metric actually exists in nature. General relativity predicts this with precision. A non-rotating black hole produces a circular shadow of specific angular size, 2.6 times the Schwarzschild radius as seen from outside. A rapidly rotating Kerr black hole produces a slightly oblate shadow with a small asymmetry related to spin axis orientation. The photon ring surrounding the shadow should be nearly circular, with brightness asymmetry caused by relativistic beaming from the approaching side of the accretion disk. In April 2019, they published the image, M87 star, a 6.5 billion solar mass supermassive black hole 55 million light-years away. The shadow was there. The photon ring was there. General relativity was confirmed. In 2023, the EHT collaboration published second epoch observations of M87 star taken in 2018. The brightness asymmetry, the hotspot where the ring shines brightest, had rotated by approximately 30 degrees from its 2017 position. The hotspot had moved around the ring by 30 degrees in 4 years. Standard relativistic magnetohydrodynamic models of black hole accretion, the state-of-the-art simulations used to interpret the original image, predict that the hotspot location should be relatively stable on year-long timescales or should show only slow drift. A 30-degree rotation in 4 years corresponds to a variability timescale inconsistent with what the standard GRMHD simulations produce. Kazunori Akiyama and colleagues at the MIT Haystack Observatory, publishing in the Astrophysical Journal, Letters in 2023, described the rotation and noted the tension with theoretical predictions. The proposed explanations include turbulent magnetic field structures in the accretion flow that are not captured in standard models, precession of the accretion disk, or jet precession driven by frame drag zigzagging from the black hole's spin. Each explanation requires parameter choices that the models do not independently derive. The first image of a black hole confirmed general relativity. The second image of the same black hole is already producing dynamics that the theories built to interpret that image cannot fully explain. We imaged the most extreme object in the universe. 4 years later, the image changed in a way nobody predicted. Number 8, the Lunar Ranging Anomaly. Neil Armstrong left a retroreflector on the Sea of Tranquility on July 21, 1969. It is still there. Since 1969, laser ranging experiments, most notably the Apache Point Observatory Lunar Laser Ranging Operation in New Mexico, have been bouncing laser pulses off that retroreflector, and the ones left by Apollo 14, Apollo 15, and Soviet Lunokhod missions, measuring return times accurate enough to determine the Earth-Moon distance to millimeter precision. The scientists doing this were not hunting anomalies. They were testing general relativity, measuring the gravitational constant stability over time, and constraining models of the lunar interior. The measurement is unambiguous. The Moon is receding from Earth at 3.82 centimeters per year. The tidal dissipation models, which calculate how energy is transferred from Earth's rotation to the Moon's orbit via tidal friction in Earth's oceans and mantle, predict a recession rate consistent with this measurement. The measurement and the model agree today. The problem appears when you run the clock backward. Project the current recession rate 1.5 billion years into the past, and the Moon arrives at the Roche limit, the distance at which Earth's tidal forces would tear the lunar body apart. At 1.5 billion years ago, the Moon should not have existed as an intact object if today's recession rate has been constant. Geological evidence says otherwise. Ancient tidal rhythmites, layered tidal flat deposits that record the rhythm of tidal cycles, have been identified in the Elatina Formation in South Australia and the Wheelie Wally Formation in Western Australia, dated to approximately 620 million and 2.45 billion years ago respectively. Analysis by George Williams at the University of Adelaide, published in Earth Science Reviews in 2000, extracted the lunar tidal signal from these deposits. The data indicates a moon at roughly 96 to 97% of its current distance 620 million years ago, not dramatically closer. The 2.45 billion year record is consistent with a moon that cannot have been at the Roche limit 1.5 billion years ago. The proposed resolution, tidal dissipation, was lower in the deep past. The configuration of Earth's continents affects how efficiently oceans dissipate tidal energy. A different supercontinent arrangement could produce lower tidal friction and a slower recession rate. The problem is that no consensus tidal evolution model simultaneously satisfies the current measured recession rate, the geological constraints at 620 million years, and the geological constraints at 2.45 billion years without introducing free parameters tuned specifically to fit the data. The most precise distance measurement in the history of astronomy produces a timeline that the geological record says is physically impossible. The measurement is right, the extrapolation fails, and the reason the extrapolation fails has no confirmed answer. Number 7, the gravitational wave echoes. Vitor Cardoso at Centra in Lisbon and his colleagues were working on a theoretical problem in 2016. What happens to the ring-down signal of a merging black hole if the interior is not the empty spacetime that classical general relativity assumes? They were not chasing LIGO data. They were exploring the theoretical consequences of quantum gravity proposals, specifically the idea that quantum effects near the Planck scale might prevent the formation of a true event horizon and instead produce an exotic compact object with a physical surface or internal structure. General relativity predicts the ring down unambiguously. After two black holes merge, the remnant vibrates at quasi-normal mode frequencies determined entirely by its mass and spin. The signal decays exponentially. Nothing follows it. The interior is causally disconnected from the exterior by the event horizon. In their 2016 paper in Physical Review Letters, Cardoso, Franzen, and Pani showed that if something physical exists inside the black hole at or near the Planck scale, a surface, a quantum structure, a firewall, the ring down should be followed by a series of gravitational wave echoes arriving at logarithmically increasing time intervals, growing weaker with each repetition as waves bounce between the Planck scale structure and the light ring at 1.5 times the Schwarzschild radius. Later in 2016, Niayesh Afshordi at the Perimeter Institute and colleagues published a statistical analysis of the first 3 LIGO binary black hole detections, claiming evidence for post-merger echoes at approximately 2.9 sigma significance. The LIGO scientific collaboration published their own analysis finding no evidence for echoes above the noise floor. Multiple independent groups analyzed the same datasets. Some found marginal evidence, others found none. The debate has continued in peer-reviewed literature through 2023 without resolution. A confirmed echo detection would be the most consequential discovery in fundamental physics since quantum mechanics. It would mean that event horizons do not exist as classically defined, that something physical lives inside every black hole. Every proposed resolution to the black hole information paradox would need revision. Stephen Hawking's final work on the information paradox, published posthumously in 2018 with Malcolm Perry and Andrew Strominger in the Journal of High Energy Physics, would require a different foundation. The echo is either present in the data at marginal significance or it is not present at all. The instruments that could confirm it are operating. The analysis that confirms it does not exist. And inside every black hole in the universe, something either is there or is not there. We cannot yet tell which. Number 6, the S8 tension. Cosmologists measuring the large-scale structure of the universe were not looking for a fight with the Big Bang. In the mid-2010s, multiple survey teams were running weak gravitational lensing analyses, measuring the subtle distortion of distant galaxy shapes caused by intervening matter, to map the distribution of matter in the current universe. The KIDS survey in Europe, the Dark Energy survey in Chile, and the Hypersuprime CAM survey in Hawaii all began publishing results around 2015 to 2017. The S8 parameter quantifies how clumped matter is on large cosmic scales. It can be derived two ways: from the cosmic microwave background, the afterglow of the Big Bang, the universe at 380,000 years old. Using the Planck satellite's 2018 data release, the Planck collaboration found S8 equal to approximately 0.834. Take that early universe measurement, run cosmic evolution equations forward 13.8 billion years using the standard lambda-CDM cosmological model, and you predict how clumped the current universe should be. The weak lensing surveys measured the current universe directly. KIDS 1000, published by Heymans and colleagues in astronomy and astrophysics in 2021, found S8 equal to 0.766. The Dark Energy Survey Year 3 results, published by Abbott and colleagues in Physical Review D in 2022, found S8 equal to 0.776. The Hypersuprime CAM results found S8 in the same range. The current universe is measurably less clumped than the Big Bang's afterglow predicts it should be. The discrepancy sits at 2 to 3 sigma, persistent across every independent survey using different instruments, different sky regions, and different systematic error budgets. The proposed explanations divide into three categories. The cosmological model is wrong in its treatment of gravity on large scales, and structure grows differently than lambda-CDM predicts. Dark energy is not a cosmological constant, but something that varies in time, and its evolution has suppressed structure growth. Dark matter has additional interactions, self-interactions or interactions with ordinary matter, that smooth out structure on relevant scales. Every proposed explanation requires extending the standard model of cosmology in ways that break something else it currently explains correctly. The geometry of matter distribution in the universe we live in disagrees with the geometry predicted by our best model of the universe's beginning. Either the early universe is giving us wrong predictions for the late universe, or the late universe is structured in a way our physics cannot yet account for. Number 5, the cosmic microwave background cold spot. In 2004, a team analyzing the first year of WMAP satellite data, led by Kate Land and João Magejo at Imperial College London, was mapping the full sky temperature pattern of the cosmic microwave background, not searching for anomalies but cataloging the statistical properties of the temperature fluctuations to compare them with inflationary predictions. They identified a region, roughly centered at coordinates right ascension 10 hours 46 minutes, declination minus 25 degrees in the southern hemisphere of the CMB sky, approximately 1.8 billion light-years across, running approximately 70 microkelvin colder than its surroundings. Standard inflationary models predict temperature fluctuations in the CMB that are Gaussian and statistically isotropic. No special direction, no anomalously large cold or hot regions. The probability of the cold spot occurring by random chance in a standard inflationary universe is less than 2%. The Planck satellite confirmed the cold spot's existence and temperature deficit in 2013 with higher resolution than WMAP could achieve. In 2015, Istvan Sapudi and colleagues at the University of Hawaii published evidence for a supervoid, a region of lower than average galaxy density, approximately 1.8 billion light-years in diameter, in the direction of the cold spot. Photons passing through a supervoid lose energy through the integrated Sachs-Wolf effect as the gravitational potential well they enter becomes shallower during the universe's accelerating expansion. Saputi's team calculated the supervoid could account for approximately 10 to 20% of the observed temperature deficit. The remaining 80 to 90% of the cold spot's temperature deficit has no confirmed explanation. Laura Mersini-Houghton at the University of North Carolina proposed in papers published in Physical Review Letters in 2006 and subsequently revised that the cold spot is a gravitational bruise, the physical imprint on our universe's geometry left by a collision with a neighboring bubble universe during the inflationary epoch. In the eternal inflation picture, multiple bubble universes nucleate and expand within a larger false vacuum spacetime. Two bubbles colliding would leave a temperature imprint on the CMB of the surviving bubble. The cold spot's size, location, and temperature profile are consistent with this prediction within the model's parameters. A confirmed bubble universe collision would represent the first empirical evidence that the multiverse exists, not as a theoretical convenience but as a physical structure that has touched our universe and left a mark. The oldest light we can observe contains a scar that the supervoid explains only partially. What produced the rest of it has never been confirmed. The geometry of the early universe is carrying a wound whose origin remains open. Number 4. The Pioneer Anomaly resolution that left a different anomaly behind. Slava Turishev at the Jet Propulsion Laboratory spent years collecting and digitizing Pioneer 10 and Pioneer 11 telemetry data that had been archived on obsolete magnetic tape formats. He was not hunting a mystery. He was trying to close one. The Pioneer anomaly had been documented since 1987. As Pioneer 10 and 11 traveled through the outer solar system beyond Saturn, they decelerated toward the Sun at a rate of approximately 8.74 times 10 to the power of negative 10 meters per second, squared above what gravity alone could account for. The leading proposed explanations before Turishev's analysis included dark matter concentrations in the outer solar system, modified Newtonian dynamics, new physics in the gravitational sector, and systematic errors in the navigation code. Each was investigated and each failed to produce the right magnitude with the right sign across the full data span. In 2012, Turishev, Toth, Kinsella, Lee, Locke, and Ellis published in Physical Review Letters a thermal analysis using recovered telemetry data showing that anisotropic radiation pressure from the spacecraft's nuclear power sources, the radioisotope thermoelectric generators radiating heat asymmetrically, could account for the anomalous acceleration throughout most of the data record. The anomaly was thermal, not gravitational. The case was declared closed, less widely discussed. The same thermal model showed residuals at specific trajectory phases. The fit was not perfect across the entire data span. The deviations were small, within the systematic uncertainties of the thermal model, and the team noted them in the supplementary material. Meanwhile, the Flyby Anomaly, affecting entirely different spacecraft with different power sources and different trajectories during Earth gravity assists, received substantially reduced attention after the Pioneer resolution. A third anomaly, the secular increase in the astronomical unit, had been identified and then disputed, with subsequent analysis suggesting it was likely an artifact of the ranging model rather than a real effect. Turishev's team partially closed the anomaly census of the outer solar system. The residuals in the thermal model remain unaddressed. The Flyby anomaly remains completely unexplained. Every solution in the inventory of spacetime geometry anomalies has revealed a smaller unexplained term beneath it. Number 3. The Hulse-Taylor binary pulsar. In 1974, Russell Hulse and Joseph Taylor were operating the Arecibo radio telescope in Puerto Rico in a systematic pulsar search, not looking for anything exotic, cataloging new pulsar detections as part of a survey of the radio sky. Hulse was a graduate student. On July 2, 1974, he identified PSRB 1913+16, a pulsar with an unusual property. Its pulse arrival times showed a regular variation that Taylor recognized as a Doppler shift. The pulsar was moving in an orbit. It had a companion, the first binary pulsar. Millisecond pulsars rotate with periods stable to 1 part in 10 to the power of 13, more stable than the best atomic clocks available in 1974. By timing the pulse arrivals over months and then years, Hulse and Taylor could measure the orbital parameters of the binary system to extraordinary precision. General relativity makes a specific prediction for a binary system of two neutron stars. As they orbit each other, they radiate gravitational waves and lose orbital energy, causing the orbit to shrink at a specific calculable rate depending only on the masses and orbital parameters. By 1979, Taylor and colleagues had enough data to compare. The orbital period was decreasing. The rate of decrease matched general relativity's prediction to within measurement uncertainty. By the time Taylor's final analysis was published in the Astrophysical Journal in 1989, 30 years of timing data showed the orbital decay rate matching general relativity's prediction to within 0.2%. Hulse and Taylor received the Nobel Prize in Physics in 1993. the first indirect confirmation that gravitational waves are real. The glitch is in what was not found.